Okay, the summer is long. I thought I would knock up a couple of videos which just recap the stuff we did with slopes, and that will take us up to and including the whole idea of friction. So let's start with a 5 kilogram particle on a smooth slope. No need to worry about friction. Slopes at an angle of 30 degrees. Remember, a particle has a mass but no dimensions, so there's no issue with air resistance. So just pause the video and see if you can label up any forces involved in this situation. Okay, so we've got two forces here. We've got the weight of the particle, which is always acting vertically, and then we have this reaction force, which is actually the force that the slope has pushing up on the particle, and that is always perpendicular to the slope. So that arrow doesn't go straight up, it's perpendicular to the slope. That's the only other force involved in this situation, at the moment anyway. Now remember, when we're dealing with slopes, rather than thinking about horizontal and vertical, it's much easier to resolve parallel to the slope, so that's in this direction here, and perpendicular to the slope, so that's in this direction here. And so the forces involved are at angles. So for example, that weight, if we're thinking about perpendicular, there's an angle here involved, and this angle here, if we're talking about parallel to the slope, there's an angle there involved, and that's the first sort of step. And I hope you can see that if that's 30 and that's 90, then this has to be 60, and this angle here, because this is a right angle, that has to be 30. And that's always going to be the case. Yeah, this angle will always be the same as this angle, and this will be 90 minus that angle. Okay, so let's now do some calculations. Now, the next question we need to ask is, in this situation, are we going to have equilibrium, where everything is balanced, up equals down, left equals right, or are we going to have unbalanced forces which result in acceleration? And in this case, I hope you can see this particle is going to slide down the slope. So we're dealing with acceleration. Well, we're dealing with acceleration down the slope. So when we're dealing with that, we are going to be using forces equal to mass times acceleration. When we're dealing with perpendicular to the slope, it's not accelerating, it's not lifting off the slope, it's not disappearing into the slope. So here we've just got forces up equal forces down. So two questions for you. What's the value of r? And can you work out the acceleration of this particle as it slides down the slope? I'm going to pause the video, see if you can remember how we do that. Okay, so let's do perpendicular to the slope. So the force up is r, and the force down is the component of this weight. And this is the key thing, isn't it? That the effect that that weight has in this direction is the size of the weight times the cos of the angle. So r is equal to 5g cos 30, so that's 42.4. And then over here, Fx is equal to ma. So there's only one force. Normally here we've got, forces going one way, take away forces going the other way, but there's only one force, and that's the component of this force going down the slope, and that's the size of the force times the cos of the angle. This time the angle is 60, so there we go, divide by 5. And this is this sort of counterintuitive thing that the weight of this particle has no effect on its acceleration, because it cancels out in the formula, and that is sort of counterintuitive. I've got two bikes now. I've got a sort of lightweight road bike, and I've also got an old touring bike I converted to an e-bike, which is much heavier. Rolling down a hill, you would feel like the e-bike is going to be going a lot faster because of the extra weight, but the maths suggests not. Now, of course, there's a lot of assumptions here about sort of wind resistance, things like that, but yeah, there we go. So that was scenario number 1. So let's now start with exactly the same situation. So let's redraw the diagram, still with a 5 kilogram mass, still at an angle of 30 degrees. But let's now say we want to apply a force here, and we want it to be holding it on the slope. Okay, so we want, so it's still a 5 kilogram mass, and it's still a smooth slope, but we want that force to be holding it in place. Okay, so we're dealing with equilibrium in this question. I hope you can see that although there is still a reaction force here, I don't actually, to answer this question, need to worry about resolving perpendicular slope. I can do it by just considering the parallel to the slope thing. So there we go. Pause the video. I haven't drawn all the forces in yet, obviously, and see if you can work out the value of P. I want that particle to remain in equilibrium, so I want forces down the slope to be equal to forces up the slope. Pause and have a go. Okay, so what are the forces pushing this up the slope? Well, that is this new force that I've introduced. What are the forces pulling it down the slope? Well, that's the component of the weight. So we've got, and this angle, sorry, and I didn't say in my introduction that that's sort of a horizontal force. Hopefully you've seen that. So that's going to be 30 degrees because it's an alternate angle. So P cos 30, 5G cos 60, and there we go. We can work out the value of the force that is needed. Okay, let's introduce some friction. Okay, so here is a rough slope. So we've got friction, and we've got a block sitting on this this rough slope, and it's not moving, but it's at the point where it's about to move, and that's a key phrase, isn't it? It's on the point of sliding down the slope, which is also crucial. This is called limiting equilibrium. So what it means is that friction, remember, friction is this magic force that opposes the motion even before something started to move. Friction magically knows which direction something wants to move. In this case, it wants to move down the slope, and it opposes that. And friction gets so far and then says, yep, I'm out. I can't go any further. And because this is on the point of sliding down the slope, we know that friction is at that value. So the maximum value of friction in any situation is the coefficient of friction, which in this case is 0.75, it's quite a rough slope, times the reaction force, which is this force here. There's another spanner in the works of this one because we don't know the angle of the slope. And that means that we've got a bit of an issue, particularly with this angle here. I mean, I know that this angle here is theta as well, but this angle here is a bit of a problem. We do have a way around it. You may remember that way around it. Friction always acts parallel to the slope, and the reaction force acts perpendicular to the slope. So those two aren't going to cause us a problem, but yeah, this one's going to cause us a problem. We've also got three unknowns. Yeah, there's a whole lot going on here that we need to be careful about. So let's use that to write a formula linking F and R. That's good because that reduces the number of unknowns. And then we're going to resolve parallel to the slope. It's not moving, so up equals down. And we're going to resolve perpendicular to the slope. It's not moving, up equals down. So pause the video, have a go. Right, so F is equal to 0.75 times R, links those two missing values. Parallel to the slope, you've got F, the friction force, which is holding it up the slope, and then the component of this force pulling it down. We don't know that angle there. It's 90 minus theta. So we could say cos of 90 minus theta, but that's the same as the sine of theta. That's where we started with all this. The sine of theta is the same as the cos of 90 minus theta. So I've got a formula for F. Resolving perpendicular slope, so that is going perpendicular, so R is pulling it up, and then you've got the component of this force, which is 3.2g cos theta. And then there's a number of ways you could go at this point. I'm going to substitute f for 3.2g sine theta up here, and I'm going to substitute r for 3.2g cos theta. So I'm going to basically rewrite that equation. F is equal to 0.75r, so that's 3.2g sine theta equals 0.75 times 3.2g cos theta. So I'm down to one unknown now. Remember, g is a constant, 9.8. But I've got a sine and a cos, and hopefully you can see at this point that we can combine to make a tan. So if I divide both sides by cos theta, now you might be saying you're not allowed to divide by cos because cos theta could be 0. Well, it could be, but it could only be 0 at this angle here is clearly an acute angle, and cos theta is only 0 at 90 degrees. This isn't 90 degrees, so we're okay. And then I'm going to divide, so I divided both sides by cos theta, I'm going to divide both sides by 3.2g. So well, the 3.2g's cancel out, that's nice. And sine divided by cos is tan, so we're basically saying that tan is equal to 0.75, and that gives us 36.9 degrees when we shift tan it. Okay, so that's the sort of problem that we've been dealing with friction at its maximum value, because this is about to slide down the slope. If it was already sliding down the slope, then this calculation would be the same, and this calculation would be the same, but this calculation would not, because the force would be unbalanced, so you'd have to use F equals ma for that one. Okay, so I'm just going to change this problem slightly. We're now going to say that there's a force pushing it in this direction, a 30 Newton force, and although my arrow is a bit wonky, that's a horizontal force. And it is still on the point of sliding, but it's about to slide up the slope. Okay, so still in limiting equilibrium. Friction is at its maximum value, but it's not yet moving. So it's a bit of a cheat really, isn't it? We don't have to worry about F equals ma because it's not yet moving, but we can put a value on friction. Up to the point of limiting equilibrium, friction is just as big as it needs to be, but once we reach that limiting equilibrium and beyond, it is this big, okay? And the key thing with this problem is because it's about to slide up the slope, friction, this magic force, knows that it now needs to hold it down the slope. It resists the motion, okay? So we're still not worrying about F equals ma, we're still having up equals down, parallel, up equals down, perpendicular, but the numbers are going to be different because we've got this additional force here. This is still going to be the same though. This is still going to be the same. So pause the video, have a go, see if you can tell me the size of the angle. It's not very steep. I've perhaps been a bit clumsy with my choice of numbers, so it's not very steep, but there you go. See if you can come up with a solution. Okay, so this was the previous problem, but now it's about to slide up the slope. This still applies, so that's still important. So parallel with the slope, there's one force pushing it up the slope, that's this one, and that's at an angle of theta, so that's 30 cos theta is the effect of that force up the slope. Two forces pulling it down the slope now. This one, which was the same before, we don't know that angle, it's 90 minus theta, so that's sine we use there. But now we've also got the friction force pulling it down the slope, so there's two forces pulling it down. Perpendicular to the slope, so there's one force pushing it up, that's R, and now we've got two forces pulling it down. We've got this as we had before, 3.2 cos theta, but this 30 Newton force is also having a downward effect, and that's the angle that we need to work out. Again, it's 90 minus theta, so that's why we use sine. What I then did, and it's not the only way to do this, so you know, some of you are much more quick on your algebra than me, I just substituted it into F equals mu r like we did before. So I rearranged this formula to be f equals, so wrote that there. This I just plugged straight in there. I then multiplied the 3.2 and the 30 by 0.75, 3/4. I suppose I could have multiplied the 9.8 as well, I chose not to. And then I just collected everything with a cos on the left-hand side. So I had that term, take away that term, and I chose to write it like this. Everything with a sign I collected on this side, so I had to add that to both sides. So you had that and that, chose to write it like that. Then just divided both sides by cos, divided both sides by that. Bob was your uncle. So, you know, those of you who remember the lessons at the end of last term will remember that's the sort of fiddly rearranging we were getting to. Let's do one final problem where we've actually got something moving. Okay, so we've got a rough slope again, mu is 0.4, not as quite as rough as before. Fortunately, we know the angle, phi, but this block is being dragged up by a force T, and it's accelerating. It's accelerating at 0.6 meters per second squared. So let's add in the extra forces that we know. So friction is going to oppose the motion. And because it is already moving, we know that friction is already at its maximum value. And that's given by that formula there. R we haven't drawn in yet, so that's that one there. We know the angles involved. This time this one is 70 and this one is 20. So we are going to resolve parallel with the slope, but this time, because it's already moving, that's F equals ma. And because it's moving up, I'm going to have the forces going up, take away the forces coming down, equals 3 times 0.6. And then perpendicular to the slope, not moving, so that's just the forces pulling it up are equal to the forces pulling it down. And I would like to know the value of T, please. Have a go. Now this is so much easier than the previous example because the force sort of holding it up the slope, previously it was a force like this, isn't at an angle to the slope, it's parallel with the slope. So that means that there's no cos or sine here when I'm dealing with the T. And because it's at right angles to perpendicular, then I haven't got to worry about it at all over here. So this is a much simpler problem. I don't know if you saw where to go from here. So we've got an expression for R here. So I can then say that F is equal to mu R. So F is equal to 0.4 times that. And then I can take that and substitute that in here. And that allows me to actually work out the value of T. Go on, one final pause and see what you get. There we go, 22.9 newtons. So yeah, that pretty much covers the stuff we did, we're getting back into pure when we go back, so we won't do any more of this. So it's probably a good thing for you to look at towards the end of the holidays or at the start. And there, I have good news for you as well. I know that there is going to be an expectation for you to do uplearn and to really sort of commit to that. But the exam questions by topic will count towards that. Those give you XP points, and XP points are the way they calculate the time. So that's a great relief to me, because maths is so much about practice that that's really where I want you to spend the most of your time in uplearn. So that's good. Right, take care. I look forward to seeing you early in September.